What if you could change your mobile app's UI without pushing a single update to the App Store? That's exactly what server-driven UI makes possible. Let's dive in. In a traditional app, every UI change means writing code, building a binary, submitting it, and waiting days for App Store approval. With server-driven UI, you edit a JSON file on your server, the app fetches it, and the UI updates instantly for every user. No review, no wait. Here's the full architecture. The control tower, our Express server, holds the UI config in update.json. When the app opens any screen, it calls getAPI screen. The screen renderer receives that JSON, reads the type field of each component, looks it up in the UI kit registry, and mounts it. The server is the brain. The app is just a renderer. Every component declaration starts with a type field. This is the only instruction the server needs to tell the mobile app which React Native component to mount. The app maintains a UI kit registry, a simple object mapping these string names to actual component classes. No type in the registry means nothing renders. The server has full control over what appears on screen. The static layer is the simplest layer. It holds hard-coded values, things like titles, button labels, or chip text, that don't need an API call. These are available the moment the component mounts, so there's no flicker or loading state for this content. Think of it as the component's default configuration that the server has baked in. The data source layer is where the real power kicks in. Each component manages its own data fetching independently. The endpoint field tells the component exactly which API to hit when it mounts. The resource ID is used to cache the response, so if two components on the same screen share the same resource, only one network call is made. The actual data returned here, revenue, users, sessions, comes straight from the server's Express endpoint. Finally, server style is where the magic of over-the-air design happens. These are standard React Native style objects. Flex direction, border radius, background color, font size, sent directly from the server and applied at runtime. Want to change the grid from one column to two? Just update, flex wrap, and width in the JSON. Need to rebrand the accent color? Change background color here. No app update, no code change. The component already knows how to apply whatever styles the server sends. This is the home screen. 3 components: a header, a chip group, and action buttons. Every chip's color, label, and navigation target comes from the server. The action field on each chip, like navigate:simplest or open_modal:quick_actions, tells the app what to do when tapped. The app itself has no hard-coded routes. The server decides where each chip goes. The simplest screen demonstrates the data source layer in action. A vertical view wraps 3 child components. The stats list in the middle has no hard-coded data in static. It's completely empty. Instead, its data source points to API Data Dashboard Stats, which returns revenue users and sessions. The component fetches this on mount independently and renders the cards. The server controls both the structure and the data. This is the grid screen. Notice, it uses the exact same stats list component as the dashboard. The only difference is the server style. By adding flex direction row, flex wrap, and width 48% to the card style, the server has transformed a vertical list into a 2-column grid. 0 changes to the app code. This is the power of the server style layer. 1 component, infinite layouts. The navigation screen shows a tabs view component. Each tab is declared in JSON with its own ID label and a components array, which itself contains a task list with its own data source. When you switch tabs, the app mounts a new task list that calls a completely different endpoint. Tasks active or tasks done. The server defines not just what the tabs are, but what data each tab loads. The carousel screen uses a banner carousel component. The layout of the carousel, how it scrolls, how images are sized, is defined in the app's component code. But the actual banner images come from API data banners at runtime. The server can swap out promotional banners, add new ones, or remove old ones without touching the app. The complex screen uses an Explore widget, a single component that renders 3 visually distinct subsections, a featured card, a row of mini cards, and a banner. All the content, titles, labels, colors, backgrounds, comes from a single API response at SDUI API data explore. The component knows how to lay out the sections. The server controls every piece of text and color inside them. The dense screen is the most complex demonstration. A single vertical view composes 5 different component types: finance header, finance card, horizontal view with 2 stats list children, and a transaction list. Some components use static data, some fetch from their own data source, and some use server style to control their size within the horizontal layout. This is the full SDUI system working together: composition, data fetching, and styling, all declared in JSON. This is the control tower in action. A single post request to API admin.update config with a JSON body replaces the entire screen configuration in memory. The next time any user's app fetches get API.config home, it receives the new config. The UI updates for every user simultaneously. No deployment, no app review, no downtime. This is the true power of server-driven UI. One renderer, infinite screens. That's server-driven UI. The server is the brain. The app is just the canvas. Every component type, every data source, every style, controlled from a single JSON file, updated in real time. No app store, no waiting, just ship. Now, let's move from the code to the actual build. We are going to run a live proof of concept to see exactly how this SDUI implementation handles dynamic updates in real time. Let's take a look.